Okay, so let's start so-called 10.6 other heat conduction problems. Well, we will consider two different kinds of problems. One of them is non-homogeneous boundary conditions. So this time we have the following problem. I have again a metal bar. Okay. Uh, and of course the temperature of the metal bar changes according to the heat equation, this equation, and we keep the endpoints at constant temperatures, but not necessarily zero. Let's say one end is kept at temperature T1 and the other end is kept at temperature T2, and again I have an initial temperature distribution. So we have the following situation. Okay, a metal bar of length L. At this end, the temperature is kept at T1, and at this end, the temperature is kept at T2. And I wonder how the temperature changes in this metal bar, given that initial temperature distribution is f of x. Okay. All right. Now, the idea is the following. Uh, Actually, it is almost the same idea we used when we considered ordinary differential equations. Remember, for a non-homogeneous equation, we suppose something like this. What we do, uh, we find a particular solution and we find complementary solution. This is the solution for the homogeneous equation, and then the general solution would be just the sum of these two, right? We will uh, actually use the same idea here. So what we need is a particular solution. Okay. Okay. Well, first we look for a particular solution for this non-homogeneous uh, boundary value problem. Okay. And the particular solution we will obtain will be as follows. It is not something actually, magical. Think of this metal bar. Okay, I keep the temperature T1 at this point and T2 at this point. As time passes, initial temperature distribution will be irrelevant, right? Let's say 2 years later, no one will remember what was the initial temperature. What will happen? This end is kept at T1 degrees Celsius and this end is kept at T2 degrees Celsius. We expect that the temperature distribution on this bar is a linear function changing from T1 to T2, right? Of course, if this metal object is an nice object, it is homogeneous in the sense that its structure is the same at all points, and we have a nice heat conduction uh, it means that you have this equation and so on. So as time passes, we expect the temperature distribution uxt converges to the so-called steady state solution, which is the linear solution v vxt. Actually vxt, but we will see that this is a function of x only, because as time passes, this solution becomes constant function of t, right? Time is irrelevant. So let's say 1 year later, it reaches to a certain temperature distribution, and after that, it won't change unless the conditions are, change, of course. Well, what is this function then? This function is the function, it's linear. At 0, it takes the value t1. At L, it takes the value t2. Okay. What is this linear function? What is this? Of course, this is just, let me just copy from my notes. You can write down the equation. It is t1 minus t2 x over L plus t1. So when you plug x equals L, so okay, first when x is 0, it is t1, and when x is equal to L, it is L over L, which is 1, t2 minus t1 plus t1, so it is t2. Well, okay, this is nice, but is this a solution of the equation? Well, note that v sub x is just t2 minus t1 over L, and vxx is just 0, and v sub t is of course 0 because there is no t variable in this equation. So it solves the heat equation, alpha squared uxx equals u sub t, because all terms are 0 for this function. So v is the solution of this equation. Moreover, it satisfies the boundary values v0 equals t1 and vl equals t2. So x is a solution of the first three equations, the differential equation and the boundary conditions. It certainly doesn't satisfy the initial temperature distribution, but that's not a problem. Okay, now let wxt to be this gadget, uxt minus v sub x. Okay, then wxx is just, when I take derivative twice, you just get this, because second derivative of V is 0, and Wt is just again ut, because the derivative of Vx with respect to t is 0, so that Wxt satisfies the heat equation alpha squared u sub xx minus equals ut, because w and u has the same second derivative with respect to x and time derivative. So here I can just write wx. Okay. Moreover, w0t is equal to what? w0t is just u0t minus v0. Well, u0t was t1, v0 is t1, so that this is 0, and w lt is equal to what? This is ult minus vl. ult was t2, vl was t2, so it is 0. Finally, what about the initial temperature distribution? Well, this is what? If I plug t equals 0, we get ux0 minus, well, vx. There is no t here. And this is f of x. And here I have the function vx. So, hence wxt is the solution of the boundary value problem. Which problem? It is this one. It satisfies this equation together with this homogeneous boundary conditions, and it satisfies the initial temperature distribution condition, where I have here f of x minus vx. Okay, now what kind of problem is this? Well, this is the problem we already considered, right? Hence wxt has a form like this. So it is bn, and from 1 to infinity e to the power minus n pi alpha over L squared t sine n pi x over L, where what is bn? Bn is just 2 over L 0 to L sine n pi x over L times f. But my f is not the original f, but it is just shifted f, so it is f of x minus v of x and then dx. So w is this. What about u sub x? The solution uxt is then what? What was this? W was u minus v. Therefore, u is w plus vx. Wxt plus vx. So, what we have obtained is the following. Let me just go over. If I want to solve this equation, okay, this is just the heat equation with non-trivial, non-zero boundary conditions. Then what we do, we first write down the steady state solution. So this is the solution. Actually, this is just the solution U when T is very large. Okay, you start this experiment, and 10 years later, the temperature distribution will be like this. Okay, the steady state solution. And then you solve this problem, which is a homogeneous equation. We know how to solve this. Here is the solution. All you have to do, compute these integrals where your initial temperature distribution F is replaced by F minus the steady state solution. Once you compute this B ends, you compute W, and then you add your steady state to W and obtain the solution of your original problem. Okay, let's do one example. Okay, so find the solution of the boundary value problem. So U sub xx is equal to U sub t. U0 t is 20, U30 t is 50, and U0x is just 60 minus 2x. Okay, 60 minus 2x. Here for t positive, and here x is between 0 and L. Okay, now this is an heat equation problem. Alpha is just 1, L is 30, T1 is 20, T2 is 50, and f of x initial temperature distribution is this. All right, we will just write down all the expressions we have computed above for this. So what is the steady state solution? State solution Vx. Okay, what was this? Let's see. Şurada yazmıştık. Evet, T2 eksi T1 x bölü L artı T1. T2 eksi T1 bölü L x artı T1. Değil mi? 0 koyduğumda T1, x yerine L koyduğumda da T2 değerini veriyor. Tamam. Yani bu da ne demek? Vx T2 ile T1'in farkı 30. L de 30. Yani o zaman burası x olacak. Ya da yazayım şöyle. 50 eksi 20 bölü 30 x artı 20 değil mi? Ne oldu burası? X artı 20 oldu. Okay. So Wxt nedir? Wxt şu. E üzeri eksi n pi alfa over L square t. Okay, Bn var tabi şurada. Bn e to the power minus n pi alpha over L square t sin n pi x over L. Where Bn is what? 2 over L 0 to L sine n pi x over L times f of x minus v of x. Okay. Dx. So let's compute this. 2 over L. L is kaçtı? 30'du. Sıfırdan 30'a sinüs n pi x over 30. F neydi? F 60 eksi 2x'ti. Bu ise x eksi x artı 20. Dolayısıyla ikisinin farkı ne olacak? 40 eksi, neyse yazayım. Okey. 60 eksi 2x eksi v'de x eksi, evet, x artı 20, yani şöyle oldu. Dx. Dolayısıyla burası 1 bölü 15 40 eksi 3x oldu. Dx. Peki nedir bu da? İntegral alırsak eksi 30 bölü n pi kosinüs n pi x over 30. Bir dakika. Dikkatli olmam lazım. So we have to use integration by parts. I consider this as u and this as dv. So okay, u times v. V is what? V is minus 30 over n pi cosine n pi x over 30, 0 to 30 minus integral 0 to 30 du is just minus 3, and then dv is minus 30 divided by n pi cosine n pi x over 30 dx. All right. All right. When I plug, okay. Rakamlar hiç hoş değil. Neyse, 30 koyduğumuz zaman x yerine 30 koyarsak burası 90, eksi 50 olacak. Değil mi? Eksi 50 çarpı eksi 30, 1500 np. 30 koyduk. Kosinüs np olacak. Eksi 0 koyduğumuzda da 0 koyarsak 40 eksi 1200 eder. Dolayısıyla artı 1200 np. Burası da kosinüs 0 just 1. Tamam. Eksi, şimdi burada 3 tane eksi var. 3 tane eksi eksi eder. Burada da 90 bölü np var. Ama bir daha integral aldığımız için bir 30 çarpı np daha olacak. 30 bölü np sinüs n pi x over 30, 0 to 30. Sinüste buraya koyduğumuzda buradan 0 gelecek. Evet, so all this term is just 0. Okay, so what we obtained is then okay, şimdi şurası şöyle diyeyim, 120'de 8 kere var. Bu 80 bölü NP olacak. 80 bölü NP artı 100 bölü NP eksi 1 üzeri N. Okay. So this is Bn. This is Bn. Yes. So Bn is just 1 over N pi 80 minus 100 minus 1 to the power N. Okay. O zaman uxt ne olacak? Bu da wxt plus vx'ti. Vx'i zaten yazdık. Vx 20 plus x'ti. Değil mi? Vx 20 artı x'ti. Evet. W'da nedir? W'da şu toplam. Birden sonsuza kadar bn e to the power minus şimdi n pi alfa. Alfa 1'e eşit bölü L. L'de 30'du. Bunun karesi çarpı T sinüs n pi x over L. Okay. Bn de bu sayı. So this is the solution. Okay. Tek mi çift mi olduğuna göre ifade değişiyor ama şurada zaten np var. Dolayısıyla n'nin bir fonksiyonu. So that's it. Efendim? Çok haklısın. Orası öyle olacak. Tamam. Evet. Yani tabii başka hatalar da yapmış olabilirim ama. Peki. Sorusu olan var mı buraya kadar? İkinci tip değişik örneğimiz de şu olacak. Bar with isolated ends. Bu ise şöyle bir problem. This time we have a metal bar. And these ends are isolated. It means that there is no heat conduction. Okay, no heat conduction at the ends. The corresponding equation becomes this in this case. So I have heat equation again. This no heat conduction means the derivative with respect to x is 0. So at the ends, 0, t is 0, and lt is 0. Okay. At the end, there is no heat conduction. So the mathematical, corresponding expression for the, mathematical expression for this physical situation that there is no heat conduction at the ends is this: x derivative of u at the ends are 0, and let's say again I have initial temperature distribution. So the difference between this problem and our original problem is that our boundary conditions are not in terms of u, but its x derivative. Okay. Well, let's see how can we solve this. We will see that the type of the solution changes drastically. So what we will do, we will go back to the beginning and start solving this using our method of separation of variables. Okay, so use separation of variables. I cannot use my previous solution because there we had this condition, u was 0 at the end, but now it is not like that. So I have to go back and go over all the steps. Okay, so use separation of variables. So I assume my solution has this form: a function of x and a function of time, and from this u sub x, x becomes again x double prime, or maybe I should start with u sub x. This is x primes t, u xx is just x double prime times t, and u sub t is just x times t prime. I plug this into the equation, so we get what? Alpha squared uxx, so double prime t is equal to x t prime. From this we get x double prime over x is equal to 1 over alpha squared t prime over t. And as before, since this is a function of x and this is a function of t, so they are functions of two independent variables. One of them is x, the other one is t, and these functions are equal. That is only possible if both functions are constants, and that constants are the same for both of them. As before, I will choose that constant to be minus lambda. Lambda is a constant, okay? And from this we get again x double prime plus lambda x equals 0, and we have also this equation t prime plus lambda alpha squared t equals 0. So we have two ordinary differential equations. What about the boundary conditions? I have this boundary condition: x prime, sorry, u sub x 0 t equals 0. This gives us what? X prime times x prime 0 times t of t is equal to 0. Okay, and this is 0. This implies x prime l times t of t is 0. Well, you see, if this derivative terms x prime 0 and x prime l are not 0, then t of t would be 0. If t as the function is 0, then uxt would be 0, and I would get the 0 solution. But we don't want the 0 solution. Okay, it's the trivial solution, but it's useless. So to get a non-trivial solution, I have to assume that these two coefficients are 0. So to get non-zero solutions, we must have what? X prime 0 equals x prime l. Both of them should be 0. Okay, so hence for x of x, we have the following 2-point boundary value problem. What is that? It is this one. X double prime plus lambda x equals 0, and then x prime is 0, x prime at 0 is 0, and x prime at L is equal to 0. So this gives us what? Let's see. Well, we write its characteristic equation. It is just r squared plus lambda equals 0. Okay. And from this, we have r is plus minus lambda minus lambda. Well, we have cases as usual. Case 1, lambda is positive. Sorry, lambda is negative. In that case, we have R1 is just the real number minus lambda, and R2 is minus this. So let's see what we get. X of x is just C1 times e to the power R1x plus C2 times e to the power minus R1x, right? R2 is just minus R1. So this is just minus R1. What are these constants? Well, I need to use my conditions, and for that I need to take its derivative. What is the derivative? So it is just C1 times R1 e to the power R1x minus C2 times R1 e to the power minus R1x. All right. Now 0 is equal to x prime 0 gives us what? Ya da şöyle yazayım. When I plug 0, I should get 0. So C1 R1 minus C2 R1 has to be 0. From this, R is of course not 0 because lambda is a negative number. So R1 is a positive number. Therefore, C1 has to be C2. So x of x is just C1 times e to the power R1x plus e to the power minus R1x, because C1 and C2 are the same. What about the second condition? X prime L equals 0. This gives us what? L yerine pardon şey yaparsak şimdi C1 çarpı ne oldu bu? E üzeri R1L artı E üzeri eksi R1L eşittir 0. Evet. Bunların her ikisi de pozitif sayılar. Dolayısıyla buradan C1 eşittir 0 çıkar. Dolayısıyla C2 de 0. Dolayısıyla da x of x is just the trivial solution. Trivial solution. Okay. What about the other case? Case 2, lambda equals 0. Well, from the equation then, r squared is minus lambda. So r is r1 and 2 are both 0. We have a double root. R1 equals 0 gives us the solution 1. So x1 of x is just e to the power r1 x. R1 is 0, so this is 1. And the second solution is just, since it is repeated, x times x1 x, so it is just x. So the solution is then x of x is just c1 times 1 plus c2 times x. And I have the initial conditions, but To apply initial conditions, I need to take its derivative. So I just get C2, and derivatives are 0. X prime 0 equals 0 implies C2 is 0. And X prime L equals 0 also implies C2 equals 0. I check both of them to make sure that there is no contradiction. If I obtain a contradiction, it means that there is no solution for lambda equals 0. But in this case, there is a solution. What is that solution? C2 has to be 0. Therefore, x of x should be just a constant. Hence, we obtain a solution. X of x should be a constant function. Okay, so in this case, we obtained a solution. All right. And then the third case, lambda is negative, so lambda is positive, so r squared is minus lambda, and from this we get r is plus minus I times mu, where mu squared is lambda, right? Because this is a negative number, its square root is just a purely imaginary number. And from this we get x of x is just c1 times cosine mu x plus c2 times sine mu x. And I need to apply the initial conditions, boundary conditions. For that, I need to take its derivative. So this is minus c1 mu sine mu x plus c2 mu cosine mu x. And so this is x of x. We apply the conditions, but let me do it in the second hour. Let me stop here.